Now we will continue with next title, but next title is a little related to 11th grade. First, I am going to talk about a part of 11th grade, which is elastic potential energy. You studied this last year. And first, I will define what elastic object mean. This definition is from your 10th grade book. It says that if an object can restore its original shape after being deformed, it is called elastic. And you are going to change the shape of an object by applying some external force. And if this object takes, when you, of course, you should remove the force. When you remove this force, if this object takes its original shape, so this object is called elastic object. So rubber, for example, or eraser, you are applying some force by your finger to eraser, changing its shape and then release it. When you release it, it takes its original shape. So eraser is an elastic object. Or a spring. When you hold a spring and then pull it, and then stretch it with your one hand, and after that, when you release it, it takes its original shape, so it's an elastic object. This is definition of elastic object. And when you compress and stretch, or when you change the shape of an object, every elastic object stores some energy, which is defined as elastic potential energy. Now, assume that this is unstretched spring and a mass M is attached to this unstretched spring. So how can I stretch this spring? If some force acts on this mass, if I pull this mass to the right by applying some force, which is called applied, this object will start moving to the right and this spring will be stretched. So in the 11th grade, you learned that if a force displaces an object by some distance, this force does work. Definition of the work, F multiplied by X. And even you calculated the magnitude of the work by F times delta X times cosine theta. So because this force, applied force by your hand, is displacing this object and causing this spring to be stretched, this force does some work, and this work causes the change in the shape of the spring, because initially spring is short, but after that, when you apply some force, it becomes longer. Yani you changed the shape of the elastic object. You changed the shape of the spring. If you change the shape of an object by applying some force, this force does work, and this work will be added to that spring as an elastic potential energy. And in the last year, in the 11th grade, you got this equation, elastic potential energy, stored in a spring, which is stretched by a distance x or compressed by a distance x, is calculated by 1/2 kx squared. K is the spring constant, x is how much you stretched or how much you compressed the spring. So keep in your mind, if you are changing the shape of an elastic object, to do that you should apply some force. This force must do some work. This work will be added to this elastic object as elastic potential energy. And for mass spring system, this elastic potential energy is calculated by 1/2 kx squared. However, when you release this object, when you remove your hand, so what will happen? Because of the elastic force, this spring will take its original shape. If it takes its original shape, what does it mean? Its energy, elastic potential energy will be decreasing. And finally, when it takes its original shape, completely its original shape, elastic potential energy will be zero. But where does this energy go? So this energy will be given to this mass as kinetic energy. Yani when the applied force is removed, spring restores its original shape. When it restores its original shape, it leaves all this excess elastic potential energy and gives this excess energy to the mass as kinetic energy. That's why this mass will start moving with some speed in the direction of the restoring force. And energy, kinetic energy of this mass will be calculated 1/2 mv squared. Yes, we learned that every spring stretched or compressed, yani shape is changed, stores elastic potential energy. An equation for elastic potential energy is 1/2 kx squared. We are not going to use this equation in any calculation, but just for answering the questions. So K is in here is the spring constant, K. X is how much you compress or stretch the spring. That's why displacement of the spring we are going to say. And according to this equation, if you don't compress or no stretching, no compression, because X is 0, if X is 0, elastic potential energy becomes 0. Yani no compression, no stretching, no elastic potential energy is stored in the spring. But if you stretch or compress the spring more and more, because X increases, elastic potential energy will increase. Yani elastic potential energy increases with increasing compression, with increasing stretching. Now, your book is first explaining one elastic object, but this is a different one. Your book is explaining this title, at the beginning of the title is a bowstring and arrow example. First, bow is also an elastic object. Why? First, in the summer course, some student told me that when a man is pulling this string, they thought that string is stretch. No, string is not stretch, because bowstring is a rigid object. Its shape does not change. It's made of steel. So this string's length will be the same as the length of this one. So string's length will not change. What is happening when this man is pulling the bowstring? This man is changing the shape of the bow. Initially, shape of the bow is something like this. When he pulls the string, this bow's shape is changing. So when the shape of an elastic object changes, what happens? So it stores elastic potential energy. Yes, bow is an elastic object. When you release it, it will take its original shape. But while this man is pulling this bowstring with some force, and then this force does some work, and this work causes the bow's shape to be changed. Because shape of the bow changed, this energy, elastic potential energy, will be stored in the bow. Yani when, I don't know if you saw these bows or not, if somebody pulls a bowstring and elastic potential energy will not be stored in the string, will be stored in the bow. Elastic potential energy will be stored in the bow. But what will happen if this man releases this bowstring and arrow? So if bowstring is released, of course bow will take its original shape. If an elastic object takes its original shape, what will happen? So it will release all these elastic potential energy, and this elastic potential energy will be converted to kinetic energy of the arrow, bow, and bowstring. Yani when the bowstring is released together with the arrow, bow takes its original shape, releases all its elastic potential energy, and most of this elastic potential energy initially stored by the bow will be gained by the arrow, because arrow is fastest. Look at the picture, the animation. You will see that arrow moves the fastest compared to the others. So that's why arrow gains most of the elastic potential energy originally stored in the bow. Why most of? Because if you look at carefully this animation, you are going to see that bowstring is vibrating. Even arrow is vibrating a little. This vibration, it's a kind of motion. Vibration is a kind of motion, and every motion has some kinetic energy, because remaining part of the kinetic energy will be converted to, the remaining part of the elastic potential energy will be converted to kinetic energy of the bow and bowstring. Why? Because they are vibrating. So, however, if you are pulling when you pull the bowstring and when you change the shape of the bow, assume that you stored an elastic potential energy of 100 joules, just a random number I am writing. So this elastic potential energy stored in the bow, yani this 100 joule, will be shared by arrow, bowstring, and bow, but most of them will be converted to the kinetic energy of the arrow. Just random number I am giving, 95 for example, 95 joule of this original stored elastic potential energy will be given to the arrow as kinetic energy. Remaining part, yeah, only 5 joule. Remaining part will be given as kinetic energy to the bow and bowstring. One more thing, this is beyond our curriculum, but remember, in the conservation of the mechanical energy, we always talk about that the force acting on the system must be conservative forces, like gravitational force is one of them. Elastic force is also conservative force. Elastic force is also conservative. Yani mechanical energy right here is conserved. What does it mean? Elastic potential energy originally stored in the bow will be equal to sum of the kinetic energies of all these objects, yani bow, arrow, and bowstring. So according to the conservation of mechanical energy, elastic potential energy originally stored in the bow will be equal to the kinetic energy of bow, bowstring, and arrow. Because mass spring system, mass of spring always changing the shape, its shape while this object is vibrating back and forth. And elastic potential energy is sometimes stored, sometimes released, stored again, released again, stored again, released again. So elastic potential energy continuously changing, as kinetic energy of this object is also continuously changing. 0 here, stops here, 0 here, maximum here, 0 here. So there is a continuous energy transfer between the kinetic energy and elastic potential energy. So now we will continue studying this mass spring system again, but we are going to study not only energy, how energy is transferred from mass to the spring or spring to the mass as kinetic energy to potential energy. Also, we will talk about how force, restoring force acting on the mass, acceleration of the mass, and also potential energy, kinetic energy, and velocity is changing. We will talk about them all. Now we are going to take different positions. So as this mass is vibrating, first I will start studying from maximum stretching, this point. Yani the spring is stretched the most. So what is this restoring force in here? What is the acceleration of the mass in here? What is the elastic potential energy of the spring in here? What is velocity of the mass in here? And what is kinetic energy of the mass right there? We will talk about this. So first position is assume that mass is pulled to the maximum displacement to x maximum and released. Of course, remember, if the spring is not vibrating initially, mass system is not vibrating initially, you have to apply some force. You should pull this object to some distance and then release that. That's the point when you release it. Okay, you are going to pull it and release it. What happens when you release this object? So first, the spring is stretched the most. Spring is stretched the most from the equilibrium position because the spring will start pulling this object back to the answering position from this point on. So if x is maximum, yes, x is equal to x maximum. Now let's start with the restoring force equation. Restoring force equation, F is equal to negative kx, tells you that first, x and force are always in opposite direction. X is to the right, look at the direction. Displacement of the mass is to the right. It is stretched. And in this case, restoring force must be in the opposite direction of the x. Yani restoring force will be to the left. So this is the direction of the restoring force. This is the restoring force. What about the magnitude of the restoring force? Magnitude, remember, restoring force magnitude is proportional to the displacement of the spring and the mass. If X is maximum, which means restoring force also maximum. So restoring force at maximum stretch point will have a magnitude which is maximum. Second one is acceleration of the mass. Acceleration of this mass. We know that according to second law of motion, force and acceleration directly proportional, and even their directions are the same. These two vectors will have the same direction. I explained them in details in section 2 chapter 1 and section 3 chapter 1. So if the restoring force is to the left, acceleration of the mass must be in the same direction of the restoring force to the left. Even because restoring force is maximum, because mass is scalar quantity, acceleration of the object also must be maximum. So at maximum stretch point, so acceleration is maximum, restoring force is maximum, both are in the same direction, in the opposite direction of the displacement, or in the opposite direction of x. And energy is scalar. Energy, elastic potential energy, kinetic energy, both are scalar. For that reason, we will not talk about direction about them. They have no direction. What about equation of elastic potential energy? Elastic potential energy equation, 1/2 kx squared. X is what? X gets maximum at maximum stretching. If x gets maximum, elastic potential energy is maximum because spring is stretched the most. If you stretch the spring the most at that stretching point, so it will get the maximum elastic potential energy. But when object is at maximum stretch at this position, this mass instantaneously stops and turns back. Look at here very carefully. So it's now start again. At maximum stretching stops. If object stops, velocity is 0. If velocity is 0, according to kinetic energy equation, which is 1/2 mv squared, because v is 0, kinetic energy also must be equal to 0. So at maximum stretching point, restoring force gets its maximum value. Acceleration gets its maximum value. Elastic potential energy gets its maximum value. Kinetic energy is 0, velocity is 0. These three always will change together in magnitude. Maximum, maximum, maximum. These two always change together, 0 and 0. However, elastic potential energy and kinetic energy, they are inversely changing. So that's why if one of them is maximum, other is 0, they are inversely changing. Potential energy, as potential energy is increasing, which means the spring is stretched more and more, object slows down. That's why its kinetic energy decreases and becomes 0 in the end. Of course, we are going to study other positions. First position, as I said, is the position, this position, we studied this. Then object will start accelerating in negative x direction. I will choose a position just between equilibrium position and the maximum displacement position. So this position. Yani object, this is maximum displacement right here. How does restoring force, acceleration, elastic potential energy, kinetic energy of the mass, and velocity of the mass changes? First, restoring force. Again, displacement is in positive x direction because the spring is stretched, and restoring force is always in the opposite direction of the displacement. That's why it's to the left. Acceleration always in the same direction of the restoring force, again to the left. However, objects, this displacement, yani x, decreasing as the object is moving to the left. Object is moving to the left because initial object was right here. So then right here and right here. So x is getting smaller and smaller. And stretching gets smaller and smaller as object is moving to the left. That's why, according to the restoring force equation, yani F is equal to negative kx equation, as x gets smaller, restoring force also gets smaller. So that's why restoring force will be increasing as object is moving towards the equilibrium position. And according to second law of motion, mass and acceleration change together. If one of them is decreasing, if restoring force is decreasing, acceleration also decreasing. Elastic potential energy. Elastic potential energy also depends on X. It depends on stretching. Stretching is decreasing as object is moving to the left. So potential energy equation tells you that 1/2 kx squared. As X is decreasing, potential energy also decreasing. As I said, these three always will change together. If one of them is decreasing, other one is decreasing. This is decreasing for mass spring system. However, if elastic potential energy is decreasing, so this energy, this decreased energy must be given to the object as kinetic energy. So kinetic energy will be increasing. Even you can get by the velocity. Look at the velocity of the object. Right here, now from this point, object stops. But later, object starts increasing in speed. That's why velocity, magnitude of the velocity is increasing. If magnitude of the velocity is increasing, kinetic energy 1/2 mv squared, also kinetic energy must be increasing. And as I said, according to conservation law, some of the elastic potential energy and kinetic energy must be constant. If one of them is decreasing, the other one must increase. They are always oppositely changing, elastic potential energy and kinetic energy. C. Now I will study the position when this mass arrives to equilibrium position right here. So let's study the position when the mass is at equilibrium position. At equilibrium position, remember, X is 0. No compression, no stretching. If X is 0, restoring force instantaneously 0. Only at this position, at equilibrium position, restoring force becomes 0 according to the equation. Remember equation, F is equal to negative kx. If X is 0, F is 0. If F is 0, acceleration is 0 according to the second law of motion. And no direction. If something is 0, of course you cannot talk about its direction. Elastic potential energy also 0 because equation tells you that if X is 0, potential energy is 0. And as I said, these three always together, changing together. 0, 0, 0. However, this excess energy released by the spring will be added to this mass as kinetic energy. Kinetic energy gets its maximum value at equilibrium position, and this mass passes from this equilibrium position with the maximum speed, maximum kinetic energy. So that's why at equilibrium position, where this position, at this position, the kinetic energy is maximum, velocity is maximum. As I said, they are always together, but elastic potential energy is 0. These two oppositely changing. One of them is 0, other one is maximum. Of course, this object will start compressing the spring. Now I'm going to choose a position just between equilibrium position and negative x maximum, somewhere here, when the object here. Yes, this time the mass starts compressing the spring. That's why displacement of the spring or displacement of the mass will be to the left. Now the displacement direction has changed. It becomes to the left. If displacement direction is to the left, restoring force must be to the right. So direction of the restoring force is to the right. Even acceleration in the same direction of the restoring force. By the time object is displacement of the mass is increasing, X is increasing. If X is increasing, according to the restoring force equation, increasing X causes an increase in restoring force. According to Newton's second law. So increasing restoring force causes an increase in the acceleration. According to elastic potential energy equation, 1/2 kx squared. As X increasing, elastic potential energy is increasing. As the spring is compressed more and more, elastic potential energy increases and increases. All these three increases as object is moving to the left and compresses the spring. By the time spring slows the object down, what happens if it slows the object down? Velocity decreases. Velocity decreases. If the magnitude of the velocity decreases, according to kinetic energy equation, kinetic energy also decreases. These two decreases, these three increases. And as usual, elastic potential energy and kinetic energy inversely changing. As one of them is increasing, the other one is decreasing. But in the end, what will happen? This object will stop. Where? At this position. Yeah, it compresses spring more and more and more, and then finally the object stops. Now I will study this position. Object passes from equilibrium, compresses spring, and stops. So at maximum compression, E, the mass is at position at maximum compression. So what will happen in this case? If the object compresses the mass the most, X is maximum, and if X is maximum, restoring force also must be maximum. So restoring force is maximum, but direction is in the opposite direction of X. X is to the left, restoring force is to the right. If acceleration force is maximum, acceleration must be maximum, and even their directions are the same. According to elastic potential energy equation, which is equal to 1/2kx squared, if maximum compression, elastic potential energy is also maximum. These three maximum. But what happens at that position? Object stops. At maximum compression, the mass stops. If mass stops, its velocity is zero. If velocity is zero, its kinetic energy is zero. This two is zero. So again, potential energy and kinetic energy is inversely changing. As elastic potential energy gets maximum, kinetic energy gets zero. So this process will continue infinitely if there is no loss of energy. Yani elastic potential energy will change the kinetic energy will change elastic potential energy back, and this change between these two types of energy will continue infinitely, and this system will oscillate between these two extreme points here and here infinitely. And summary. So three positions. One position is maximum stretch. Positive X maximum. This is maximum stretch. One position, maximum compression. So at these two positions, restoring forces are maximum in here and in here. Only directions are opposite. Accelerations are maximum, directions are opposite. Elastic potential energies are maximum at these positions. Yani these three are maximum at maximum compression and at maximum stretch. However, while these three maximum, other two becomes zero. Yani because in here object stops, in here object stops at maximum compression and at maximum stretch, velocity is zero, and also kinetic energy is zero. But at equilibrium position, because X is zero, no compression, no stretching, equilibrium position, restoring force is zero, acceleration is zero, elastic potential energy is zero. While this three is zero, other two is maximum at equilibrium position, which is the kinetic energy, which are kinetic energy and velocities. So this is all about the characteristic of vibrating mass spring system.